All right. Yeah, hi everyone. My name is Cristi. I'm from BFL. This is joint work with Sigal Oren. It's called Planning Against a Prophet, a graph-theoretic framework for making sequential decisions. Now let's think of the following situation. We have a house. We want to allocate to some set of agents. These agents arrive one by one. They have a value for this house, and whenever the agent arrives, you have to decide whether we give the house to this person. This would be the classic profit inequality problem, right? But now let's say on top of selling the house, we could rent the house for some time. All right. So whenever the person arrives, they not only tell us how much they would pay for buying the house, they also tell us how much they would pay for renting the house for any number of months. So maybe for 1 month, it's $10. For 3 months, $25. This is very affordable housing. For 1 year, all right. And then this means that we have to choose some length. We get the $25, and then the house is unavailable, right, for the next 3 months. We cannot allocate the house to these people, but then after 3 months we can allocate the house, right? So to be more precise, let's say we have 1 agent per period. Each agent has a value for each possible length. These values are independent, drawn from known distributions F1 to Fn. When the person arrives, we observe these values, we choose the length of the state. I want to maximize the expected sum of the values of the people we allocate, and we compare against the best allocation in hindsight, like in the profit inequality. As I said, this captures the profit inequality in the case where we can allocate only to 1 person, and for that we can do a 1/2 competitive algorithm. But it also captures this other model. There's this paper in EC last year by Adams, Fishman, and Schmann that looked at this same model, but in the special case where values are IAD, that means all distributions are the same, and the value for a stay or lease of length t is given by some value per period. So t times the value. So its value is just given by a value per period, right? And for that, they gave a 0.396 competitive algorithm. Now, I say that it's much better to think of this problem in the following sense, in a graph. So what would that mean? We put a node for each period. We draw an arc for each node going to the right, which means we don't allocate this person the house. And these curved arcs represent giving this person the item for so many months, for so many periods. So if we give the item to this person for 3 periods, that means we have to skip 3 nodes. Okay? And then the model goes as follows. We start in the first node. We see the values of the arcs, and we choose 1 arc. We collect this reward then. Then we observe the values of the next arcs, and we take 1, and we get the value of 200 until we reach the last node. In this particular realization, we collected a value of 210. And now there are some realizations we didn't see, but let's say they're these. So the optimal decision would have been to first choose 0, and then 200 and 150, and we would have 350. And thus in the profit inequality, we want to maximize the expected total value we collected along the path, and we compare with the expected value of the best. And we show that we can get a one-half competitive algorithm for this particular instance, type of instances, which generalizes the profit inequality and also improves upon this 0.3, something of last year, which was also for a more restricted set. Now the proof is kind of simple. If you are familiar with OCRS, online contextual resolution schemes, you will understand pretty easily this proof. If not, I will show you the proof now. So the algorithm is as follows. Independently at each node, we simulate what opt would do. That means we look at the values, we draw some fresh samples of every other arc, and we mark the arc that opt would use from this node, if it uses some arc from this node. And we mark it as tentative for a. But then on top of that, we toss a coin with some parameter alpha I. If the coin comes up heads, we take the tentative arc. If not, we just continue to the right. Now, this is the whole algorithm. We just have to define these coins, right? Now, if I denote by xe the probability that the optimum path takes arc e, we will set this parameter alpha I to be 1/2 divided by 1 minus 1/2 times the sum of these probabilities over this set E minus I, which I define as the set of arcs that skip node I, right? To jump over node I from an early node to a future node. My first claim is that this is well defined, right? Like we need this to be a probability. So I claim that alpha I is between 0 and 1. Now in this graph, it's very easy to verify this, right? Remember that opt takes a path. So these xe are just a complex combination of paths. So it's a flow. And therefore, since this set E minus I is a cut in our graph, the sum of these probabilities has to be at most 1. So the algorithm is well defined. Now let's prove that that gives a 1/2 approximation. I claim that conditional on an arc being a tentative arc, we selected probability exactly 1/2. And this, if we prove this claim, then we are done because because every tentative arc is drawn according to opt, and we're taking in the probability 1/2, so we get half of the value. We do this by induction. The base case is that every node departing from the starting node satisfies the claim, but this is very easy because no arc jumps over the first node because it's the first node, right? So the parameter is exactly 1/2. Now for later nodes, let's assume all previous nodes satisfy the claim. That means that the claim is true for every arc in this set E minus I, because by definition they come from previous nodes, right? And now I claim that the denominator in this parameter alpha I is exactly the probability that we visit node I, right? And this is because the probability of visiting the node is the probability of not jumping over it, which is the probability of taking some arc in E minus I. But because it's a cut, we can only take one arc of this set. So these are these joint events. So it's just the sum of those probabilities, and by the induction hypothesis is 1/2 times this, right? And now what's the probability that we take the tentative arc? Is the probability that we reach this node, which is this, times alpha I. And therefore, this cancels with the denominator and we get the value. All right, so that's the 1/2 competitive algorithm. This is the proof using this OCRS. Now, if we have this graph model, what stops us from looking at a general graph, right? So why it has to be one path with jumping? We could have more general directed graphs. So let's say we have detected a cyclic graph with a starting node S and a destination node T. We have values on the arcs. They are independent across nodes. Maybe they are correlated if they have the same tail, but if they have different tails, they are independent. We want to go from S to T, and we collect rewards along the way. We compare against the best path in hindsight. So we start with the first node, set all the values. We take one. We observe the values, take one. Observe values, take one until we reach the last node. Well, let's skip this. And our result is the following. If k is the width of the DAG, the graph, where width means the size of the largest anti-chain, or equivalently, the smallest number of paths I need to cover all nodes in the graph, not necessarily all arcs, but all nodes. Then we can get the 1/2k competitive algorithm. Well, in the previous example, k was 1. In this example, k was 2. And so we get a guarantee for every possible graph parameterized by the width of the graph. I won't show you the proof, but I will tell you that we don't know whether it's tight, our result. We only have this upper bound. We know that no algorithm is better than 1/k+1 competitive. The example is very simple. It's just this graph, where every option has expectation 1. So for the Oren algorithm, there's nothing we can do. We just get 1. But after we take one step with the 0, we have these long shots that have some very high value with small probability, so still expectation 1. But for the optimal solution, this is very good because it can take almost the sum of all expectations, and in this case, it's k+1. So no algorithm is better than 1/k+1 competitive in this model. And we don't know if it's tight, but we know that if we have these joint paths in the graph, meaning that we can decompose, we can cover, the graph into k paths that don't share nodes except for S and T, then we can get a 1/k+1 competitive algorithm. Right, and yeah, we think this is a very nice model that extends this idea of perfect inequalities to planning problems, right? So we have to decide, make decisions, and we have different options, right? But also it's nice because it can be integrated with other models in perfect inequalities very easily. So this is one extension we have. Let's say we also have some non-reusable resources, which let's say are labels in the arcs. So for instance, here I have an arc which has 2 labels, a black label and a red label, and some other arcs. This one's a blue label, a yellow label. And we have constraints on how many arcs we can take for each label. So we can take at most 3 red arcs, at most one yellow, and so on. So apart from being a path, we have to satisfy the constraint that we don't use more than so many arcs for each label. Right. This can model different things, but one nice example is this. Let's say we have a repair shop. We have some parts, right? And people come, and not only we have to serve them for some time, blocking the shop, but we also have to use these parts, right? So we have these constraints on how many parts we have, right? So how many requests that use this part we can serve. And for this kind of model, we can prove the following. If no arc has more than D labels, then there is a 1/k times D+2 competitive algorithm where K is the width, and D is the maximum number of labels an arc has. So it's not the total number of labels, it's just how many labels an arc has. And again, I don't claim this is tight, but for remember, for K equals 1 and D equals 0, we could do a 1/2, and that was tight. When we go from D equals 0 to D equals 1, we step away from the 1/2. We have an example where no algorithm can do better than 4/9. Yeah, all right. So to finish, what you have is this nice planning model in this profit inequality framework. And we can get some non-trivial guarantees, as I showed you. Even for this case, K equals 1, we obtain the 1/2, which improves upon this result of last year. As I told you, the model integrates well with other combinatorial constraints, such as matching. Like for D equals 2, this captures matching profit inequalities. So it integrates well with other constraints. Yeah, so in future directions, our results for K larger than 1 and P larger than 0 are not tight, I think. I don't know what would be the analogous to random order or free order in this kind of model, because we have a graph and it's kind of pixels, so I still don't know how to integrate that there. And this is incomplete. But the question was, can we model the case where we have multiple reusable resources? So in the first example, the house you can think of as a reusable resources. The labels are like non-reusable resources. Can we have more than one reusable resource? Yeah. So that's it. Thank you.
We have time for questions.
Yes.
I don't know if I missed it, but did you have any assumptions on the edges coming out of a certain node, like they have to be increasing in length or anything like that?
No.
They can be out there.
Yes. Because in the general model, also there are no. I mean, there's no length. The length is not well defined. I mean, you can draw a topological order, but there could be many.
When you said the house model, I thought, oh, they have to be like the value over the length has to be decreasing or something.
No, to get the 1/2, it doesn't have to be. I guess, I mean, you can only do that.
Yeah.
So the feasibility constraint here is basically you have a bunch of sets, and from every set you can only choose one. And in your case, it's you have a bunch of cuts, and from every cut you can almost choose one edge, right? But what's special about cuts? Like, can you generalize into more to capture more things?
Yeah, it's a good question. I don't know.